I will just switch off my camera because I have to turn the laptop. So okay, so I will just start now. Just once confirm when that I am audible and you can see my slides last time so that I can start properly.
Sir, you are audible and we
Okay,
can see your slides, sir.
okay, thank you. So okay, so uh, uh, a very good evening all, and welcome to the NPTEL problem solving course. The course is coordination chemistry, so which is taken by Professor Debasis Ray and myself Satya Prakash Yadav, a PMRF scholar from August 2020 batch to present. So I am currently working with Professor Satish Patil uh, in SSU department, Indian Institute of Science, Bangalore. So first coming to the this about the course. So this is the 12B course. So in the first B, basically professor will introduce about the base like how this coordination compound came into the pictures, and then he will slowly go to the classification of the ligand, and then in week 2 he has described about the nomenclature, what are the rules and rules for the nomenclature, and week 3 he will discuss about the coordination number and stereochemistry related to the coordination complex, and in week 4 he will discuss different types of structures, symmetric isomerism and coordination equilibrium. Then in week 5 he will just discuss the different kind of bonding theory in the complexes, like valence bond theory, crystal field theory, and ligand field theory and all like that. And then he will use the crystal field theory to explain the John Taylor effect and spin crossover, and also to use the like crystal field theory to describe the color and optical spectra of the organic complexes, and what is the role of the Argel and Tanabe-Susugano diagram to assign the peak in the electronic spectra of the coordination complex. And then he will discuss about the magnetic property of the coordination complex. And in week 11 he will discuss about the like ligand field theory, what is sigma and pi orbital, basically in the where we have this sigma donor and pi uh, acceptor kind of ligand. And then he will discuss about the reaction reactivity and biological inorganic chemistry, and finally he will close with the structure, symmetric isomerism and coordination equilibrium. So in week 1, so there are 3 lectures. In lecture number 1 he has introduced about the coordination complexes, then basic definition he has introduced us, and he has gone through the classification of ligand 1. So classification of ligand 2 and 3 it will come into the next week, but I will slowly discuss. So first I will briefly go to the like how like coordination chemistry came into the picture. So I will just take some 10-15 minutes to describe how it came, and then finally I will go to the problem solving session. So first of all, what is the addition compound? So addition compound are of two types. First one, those which lose uh, their uh, their identity in solution. So basically they are called double salt. Second one, those who retain their identity, they are called the complex compound, right? So in the double salt, what we have, basically we are we are putting two or more stable compound in the stoichiometric amount, and basically we evaporate, and then finally we get a crystal. So these are double shot. Like suppose we have this K2SO of potassium sulfate plus aluminum sulfate plus 24 water molecule. If we crystallize it, basically we will get the K2SO4 dot Al2SO4 thrice dot 24 H2O. This is called potash alum, right? So once we are dissolving in the solution, you will get all the ion, potassium ion, sulfate ion, and aluminum 3 plus ion. So all this ion you will get in the solution. But what about the complex compound? So basically, suppose if we are mixing, like I will come into the detail when he has used the, like basically cobalt chloride plus ammonia solution. So he formed some kind of, suppose he used this 6 ammonia solution, so he formed some compound like CO NH3 6 Cl3. So once he dissolved in the solution, he got this cobalt 3 plus Cl, like he get the basically 3 Cl minus. But once he went to the 5 NH3, he has not get the all the Cl with the in the solution with silver chloride once he has used. So if we see that, so Berner proposed number of the color complexes of different kind of metal, basically cobalt, nickel, iron, platinum, platinum 2 plus and platinum 4 plus, etc. So what is the Werner? So Werner started work in 19, so I think I have written wrong. So its work went up to 1919, and he got the Nobel Prize in 1913 for his Werner theory. So what like upon what things this Werner theory based on? So he has basic use the reactions of the complexes, reaction of complex. Second thing, he has used the conductivity measurement, and third, he has used the isomerism. With this, he has given two theory. First thing, he has said that this complexes has two types of valency. One is the primary valency. So this is ionizable, important thing, and non-directional. Second, he has used the secondary valency. So these are non-ionizable, and these are directional. So this theory he has given. So how he has given this? So he has taken cobalt chloride with different like stoichiometry of ammonia. So he has taken 6 ammonia, 5 ammonia, 4 ammonia, and 3 ammonia. So what kind of complexes he got? So some minute, let it got hang. So what kind of complexes he got? He got basically your cobalt chloride dot 6 NH3 and cobalt Cl3 dot 5 NH3, cobalt Cl3 4 NH3, and finally he got cobalt CNH3 3 NH3. Right now he don't know about what kind of structure it forms. So what he did, he has put in all the solvents, suppose he has cobalt 6 NH3, 5 NH3, 4 NH3 and 3 NH3. So once he put that silver chloride, so what he get? He basically here get 3 AgCl, here he get 2 AgCl, and here he get one AgCl, and here no precipitate of AgCl. So what he thinks that there are two types of valency. One is the primary valency and other is the secondary valency. So how he has said, basically he has given the inner sphere concept and outer sphere concept. So how he has written CO NH3 6 Cl3. So this is secondary valency which is satisfied by ligand, and this is the primary valency. So later he has given CO NH3 5 Cl and then Cl2, CO NH3 4 Cl 2 Cl, and finally CO NH3 3 Cl3. Okay, so another way how he did, he saw that conductivity is decreasing once he is going from 6 to 3. Why? Because once we are using lesser equivalent of ammonia solution, basically here we have 3 Cl minus plus 3 plus ion, here he has 2 Cl minus, here he has 1 Cl minus, and here has no. So this is like a non-conductive solution, right? So basically he has 4 ion, 3 ion, 2 ion and 1 ion. So accordingly he got the conductivity. So from here only he has given there are two types of valency. One is the primary valency and second is the secondary valency. So he has given that inner sphere concept and outer sphere concept. So another thing is that he has based on the color. So this is, suppose this is orange yellow, this is purple, but this has two color. One is that green and second is the violet. So basically from here he said that there are two types of isomer. One is the cis isomer and other is the trans isomer. I will come later how this. So this, from the isomerism he has explained that all the complexes and given that theory of primary valency and secondary valency, and he has given the inner sphere concept and outer sphere complex. Okay, so I will just briefly go through what professor has told you about. So his work evolved from 1860 to 1990. A Swedish chemist. He worked on compound composed of cobalt third chloride and ammonia. So he has taken the different stoichiometry of ammonia 5, 4, 3 and got the different kind of complexes. So based on the based on conductivity measurement and isomerism and reaction, he has given that inner sphere coordination sphere and outer sphere complexes, right? So in inner sphere the valency is satisfied by the neutral or anionic compound, and it is called the coordination number, where outer sphere is basically satisfied by the cation or anion, and that is given the primary valency. Okay, so what is the special about this kind of compound? So basically here observe is the transition metal complex, that is the first thing, and color depend on the central atom, oxidation state and type of ligand we are using. So these things we will come into the detail once we will go to the lecture number which lectures, I think here, color and optical spectra. Then we will see the what is the effect of metal ion. So basically in metal ion the charge and size ratio, and ligand, what kind of ligand is there, how their spectra change, we will discuss there in detail. Okay, so these are like different kind of color once we are changing the ligand. And what is the special about D block element, why they are forming the coordination complexes? So the first thing is that the incomplete D subcell, that is the most important thing about the transition metal. Because of that only they are giving this coordination property. So this is little bit about the transition metal. So here is that not all D block element have the incomplete D subcell, For example, like zinc, it is already D10 and 4s2. It is typically not considered as a transition metal ion. Or suppose this is scandium 3 plus, which has a stable argon configuration. It also have no d electron. But so actually, what is the definition of transition metal? So it has the at least one ion. That is the most important. At least one ion will have the partially filled subshell of d electron. Okay, so these are the different thing he has shown how the colors come into the pictures, and then he describes about the classification of ligand and what is monodentate ligand, what is bidentate ligand, tridentate ligand. Those things I will come into the detail once it will come to the problem solving session. So these things it will come. So now your involvement come into the picture. So the first question is, how many non-bonding orbital available in the NH3 molecule? So if you people have gone in the lecture number first, so I think in within 10 minutes these things has come into the pictures. So can anyone write in the chat box how many non-bonding orbital available in the NH3 molecule? Okay, so you are okay saying matlab option C is correct or option A is correct? Option C. Any other one who has different opinion than ma'am? Okay, so ma'am is actually right. So option C is correct. So let me write about NH3. So this is N H H H. So basically nitrogen has 5 electron. So 3 electron will be shared by proton and one lone pair will be there on the nitrogen. So it has 3 bonding pair plus 1 lone pair. So the geometry is tetrahedral, but once we are talking about the shape, so shape is nothing but in geometry you remove the lone pair. So this is trigonal. So the option C is correct. Okay, if anyone has any doubt he can ask me, otherwise I will go to the next question. Okay, no problem, I will go to the so what is the species generating when we are reacting cobalt NH3 6Cl3 react with the moist Ag2O? Can anyone tell me the answer of this second number question? In between I will just check that whether recording is on or not. Yeah, fine. Can anyone just write in chat box what is the answer of question number 2? Any guesses? Can anyone guess like what will be the answer? Am I audible? Can anyone just confirm that am I like I'm audible at least?
Yes, you are audible, sir.
Okay, so anyone can give the answer for question number 2. Just guess what can be formed if we react cobalt NH36 like hexaamine cobalt third chloride reacts with moist Ag2O.
3 mole of AgCl should be formed, sir, but there is no such answer option there.
Can you repeat once again?
I think 3 mole of AgCl will be formed, but there is no any option there, sir.
Okay, okay. So I will just come in on that. So okay, so let me explain. So the answer is B. How? So we have this CO NH3 6 Cl3. So we have Ag2O plus moisture HgO. So what will form basically your CO NH36, okay, OH thrice plus, okay, AgCl, okay, another thing what it can form. Okay, so basically what will happen?
Yes,
Hello,
yes, sir. Got it, sir.
got it right? So basically what will happen, your at will you form AgCl only. So this is the initial when Werner is trying with different kind of reaction. So he used this silver plus, he used Ag2O, different kind of reaction, and he wanted to find out what kind of complex is it. So whether reaction is happening in the inner sphere or outer sphere. So this will happen only the outer sphere. So this OH basically will replace the Cl minus. Got it? Okay, so you can just balance it out. So the correct option is B. So if anyone has any doubt, I can just balance it also. Otherwise, you can go and try by your own how you can balance it. Okay. So the question now 3. Among the following, which ligand can act as a ambidentate ligand? Okay, so ma'am is asking, sir, why not the reaction happen in the inner sphere? Okay, so that's what like I told you in the initial. Once I am explaining about the Werner theory, so he said that this is the simple ionic reaction, ion exchange reaction. So basically, your Cl3 will replaced by the uh, uh, OH. Why? Because we are using the Ag2O with moisture. So what is happening? This inner sphere is basically non-ionic and directional, right? So this is stable. So only thing you can replace that anion with this Ag2O and H2O. So this only primary valence can get it. You can you can also do the reaction in the inner sphere also. Like suppose one condition I am forgetting. So under oxygen, if you heat it, so basically this will decompose into CO2O3. So if you interested, I will give that reaction also, but currently I like not. So basically if you heat it at 100 degree centigrade, under O2, so this compound will form. So reaction will happen, but this is the simple ionic reaction where this silver plus ion will form the precipitate silver chloride, and this OH basically it will form OH3. Okay. So among the following, which ligand can act as a ambidentate ligand? So option is C6, like triphenyl phosphine or triphenyl phosphine oxide, or diphenyl sulfoxide. Option D is null. Can anyone just write in a chat box what will be the answer for this question? Okay, Devendra Malik is saying C. Okay, so any other one has any other opinion for this, or others also agreed with Devendra Malik? Okay, ma'am is saying D. Okay, so Devendra, can you tell me what is the ambidentate ligand?
Which have two active site, either like CN, either carbon can form bond or nitrogen can form bond.
Yeah. So basically it has two coordination site, but at the time it can bind through one site only. So that is called the ambidentate ligand. So yeah, Devendra is right. So now I will explain why others are not there. So we have first is, sorry, 1 minute. Okay, first we have pH. Okay, so this we have. So here we have only one coordination site, which is our phosphorus atom in PPS3. Second we have C6, like if I write P, pH, H, we have. So here in phosphine oxide we have only one coordination site, which is oxygen. But once we go to that sulfur, oxygen, pH. So basically it is a DMSO, dimethyl sulfoxide. Instead of methyl we have phenyl. So what is happening here? We have two coordination site. It can bind through oxygen, it can bind through the sulfur. So but why not phosphorus? Because here we don't have any other like extra lone pair, but here we have one lone pair in the sulfur, because sulfur has 6 electron. So 4 involved in the bonding and one lone pair it is having, through which it can coordinate to the metal. Or oxygen has also 6 electron, so 4 electron, 2 electron it has bind through the sulfur, and 2 lone pair is there, but oxygen can only donate 1 electron pair. Okay, so this is not there, this is also not there, this is not there. The correct option is C. Okay, so ma'am, did you get that why the option C is correct? Then I will move to the question number 4. Yeah, so how many chromium oxygen bond present in the dichromate anion? So I think professor has discussed in some lecture of any of 3 lectures, where he is describing about the various oxidation state present in the transition metal. So in that he has also described like how many he came across the dichromate. So how many CRO bond, cobalt oxygen bond, chromium oxygen bond present in the dichromate anion? Can anyone write in the chat box? Okay, Dr. Naveen Awasthi saying 6. Okay, any other one who has different opinion than sir? Okay, Devendra Malik is saying 8. Ma'am is also saying 6. Okay, it's two contradicting. So let's see, like how many chromium oxygen bond present in the dichromate. So our dichromate is CrO7 minus 2 minus, right? K2Cr2O7, right? So we have O bridging Cr, then we have double bond O, O minus, double bond O. So how many CrO bond present is there? 1, 2, 3, 4, 5, 6, 7, 8. So the correct option is D. So I think Devendra Malik is right. So how many chromium oxygen bond present is dichromate ion is 8. Okay, I think others has got the answer, like how many chromium oxygen bond present in the dichromate ion. Okay, then I will move ahead to the next question. Okay, so in the complex formation, central metal ion act as Lewis base, bronze base, Lewis acid or Bronsted acid. So can anyone tell? What is the correct answer for question number 5? Okay, Dr. Naveen Awasthi is saying okay. Devendra Malik also C. Okay, great. So yeah, so if anyone, okay, yeah, someone raise hand. Rupali ma'am is raising hand. Can you tell me any doubt? Okay, so in complex formation, central metal ion act as a Lewis acid. So the question is why. So if we see like metal to ligand bond, so basically ligand is donating one lone pair to the metal. So lone pair donor is basically Lewis base, and lone pair acceptor is called Lewis acid. So this is the Lewis acid base concept, where like if a species is donating one lone pair, they called Lewis base. If they are accepting lone pair, they are called Lewis acid. So in coordination complexes, metal has this vacant d orbital in which basically ligand will give their lone pair to the metal. So the correct option is C. I think everyone has got this answer correct. So I will move to the next question. So which of the following can act as a chelating ligand? Can anyone write in the answer chat box what will be the answer for this question number 6? Okay, Dr. Naveen Awasthi is saying C. Okay, anyone else? Okay, Devendra Mala. So can anyone just give some hint what is this NH2 CH2 CO2 minus? So what is it called? NH2 CH2 CO2 minus? And like what is the coordination sites in this NH2 CH2 CO2 minus? Yeah, correct. So it's called glycinate. Right. So yeah, fine. So just I will tell others. So chelating agent are those who form a chelate. So basically the property of the chelating ligand is they should be polydentate ligand. They should be having two or more donor sites. So in SH minus we have only one donor site, that is sulfur. In H2O we have one donor atom, that is oxygen. In SCN minus we have these two donor, but at the time only one can donate, either nitrogen or sulfur. This is called ambidentate ligand, we discussed previously. But something special about this NH2 CH2 CO2 minus. So this is called glycinate. So how it forms? So basically suppose we have metal, so it has like we have this NH2, we have CH2, we can sorry, I can write somewhere else how it forming. So we have M, N, we have O, so you can write C double bar O. So this is minus. So basically it has two donor sites. One is the nitrogen lone pair, another is the oxygen minus. So basically there are different kind of glycinate salt, like copper salts, copper complex of the glycinate. So these are called chelating agents. So they have two or more donor sites. So in this case we have two donor sites and it's form a chelate. So basically there are others like EDTA, other kind of chelating ligand also are there. So the correct option is C. I will come into the EDTA. I will like detail structure I will draw and I will show you how it is chelating. Okay. So going to the what is the coordination number and oxidation state of cobalt metal. In cobalt, NH3 to H2O to Cl2 plus. Can anyone just write in chat box? Or question number 7. Okay, Devendra Malik is saying D, ma'am is also saying D, or Dr. Naveen Avasthi is also saying C or D. Okay, let's me calculate. So what is the coordination number? So coordination number is simply that how many donor sites giving that like basically it's a through how many donor site it has binded. So we have this two nitrogen atom, two oxygen donor and two chlorine donor. So the coordination number is basically 6. This is called secondary valency. And now once we calculate the what is the oxidation state of cobalt. So suppose I will consider the oxidation state of cobalt metal is X. Then NH3, it's a neutral compound, so its oxidation state will be 0. 2 multiplied by 0 plus, so we have this H2O. This is also a neutral compound, it has oxidation state 0. So 2 into 0 plus, it has 2 Cl. So basically chlorine has 1 minus, so we have minus 1, which is overall equal to what is the whether is the cation or anion or neutral. So that will be the on the right hand side. So this is plus 1. So now x minus 2 is equal to minus plus 1. So basically x is equal to plus 3. So yeah, the correct option is D. So I think others also has got the what is the answer for the question number 7. Now I will go to the question number 8. What is the oxidation state of chromium in chromium NH34 Cl2 plus? So I think this time others should also tell what is the oxidation state of chromium. They can calculate and just tell. Okay. Yeah. At least one new member, Rupali ma'am, also had said that. So yeah, that again I think. Let me go quickly. So suppose the chromium oxidation state is X. So 4 into 0, because for neutral compound oxidation state is 0. 2 into Cl minus H minus 1 is equal to plus 1. So basically X is equal to plus 3. So this is correct. Let me go to the so ethylene diamine. So ethylene diamine tetraacetate ion. So EDTA4 minus is a ligand with denticity. So option A is 4, option B is 2, C is 6, D 5. Okay. Rupali is saying A. Devendra Malik is saying Dr. Nasser. Okay. Okay. So yeah, another like other way to ask questions, how like what are the like donor sites, how many nitrogen, how many oxygens are present in the EDTA. Can anyone just write in chat box how many nitrogen donor, how many oxygen donors are there? Then I will write the structures. Okay, N2O4. Yeah, fine, correct. So basically EDTA, where it has importance, it has like importance in analytical reagent. So suppose we are calculating the hardness of water, so there basically we use the EDTA. So what is the EDTA? Is ethylene diamine tetraacetate ion. So in this, suppose we are forming this calcium EDTA. So how the structure look like? So we have in center calcium, we have nitrogen. So this is ethylene diamine. Now we have to write the 4 acetate ion. So how it will go? It will go here. So this 1 acetate, second other way it will go to like this, third will come here. So this is kind of octahedral arrangement will be there in the calcium EDTA structure. So we see the calcium EDTA or magnesium EDTA, this kind of octahedral. So it has 6 donor sites, means denticity is 6. So 4 oxygen, which is the coming from the acetate ion, and 2 from the nitrogen. Okay, so the option C is correct for others. Coming to the question number 10, what will be the coordination number and oxidation state of FeCl2 in water? Can anyone just tell what will be the coordination number and oxidation state of FeCl2 in water? Okay, Devendra Malik is saying B, Dr. Naveed Awasthi is B. Okay, yeah, correct. Okay, So can I ask the next question? What will be the okay for the time being, because next question will come on to that only. So yeah, so this basically in the first instant it will form FeH2O6 and then Cl2. So the correct option is B. Later it will come why it is less stable and what will be the final product, final complex compound, that I will come later. So I will not ask the question now, at least. Let's go to the question number 11. In ammonium solution of cobalt chloride, the first sphere of attraction and second sphere of attraction are observed by ammonia molecule and Cl minus ion respectively, Cl minus ion molecule and ammonium molecule, this is not ion molecule respectively, water molecule and Cl minus ion respectively are only ammonia molecule, this is ion. Okay, can anyone just write in the chat box what will be the answer? It's okay. Dr. Naveen Avasthi is saying A. Anyone else has different opinion? Okay, Devendra Malik is saying B. Two different opinion. Anyone else? Anyone else? Okay, now I got where like Devendra Malik got confused. So what is the first sphere of his attraction? Basically here it is discussing about inner sphere. Second sphere of attraction is basically the outer sphere. Okay, so inner sphere means secondary valency, talking about the secondary valency. Outer sphere means talking about the primary valency. Okay, now can anyone tell like which is the correct answer? So if we see that cobalt chloride in ammonia solution, so basically we have cobalt NH36 Cl3. So this is your inner sphere, this is your outer sphere, or you can say secondary valency and primary valency. So the correct option is A. Okay, let me go to the question number 12. In hemoglobin, the metal ion present is manganese, copper, iron, or iodine. C. Okay, Devendra Malik is saying C. Dr. Naveen Avasthi is also saying C. Anyone has different opinion? Okay, so yeah, so the correct option is C. So we will discuss detail in the next lectures when we will discuss about the biological ligand. So there we will discuss about what is the porphyrin ring, what is the coring ring. So all those things we will discuss detail in the next week lecture. So there once we will go to the classification of ligand, I think in the ligand third, there professor has discussed about the biological ligand. So we will discuss there what is the porphyrin ring with the iron in hemoglobin. Okay, so the correct option is iron. Okay, let me go to the next question now. 1 minute. So what is the final product of hydrolysis of FeCl3? Okay, can anyone tell? Can anyone just tell what is the final product of hydrolysis for FeCl3? Okay, ma'am is saying B. Okay, anyone else? Devendra Malik is saying A. Dr. Naveen Awasthi is saying A. Okay, so I think this is in the lecture number first only. So what happens if we put Fe3 plus ion, like Fe3 solution in water? So basically first it will form Fe H2O 6 3 plus. Basically here we have 3Cl minus, so this is balance. So that this is the initial product which is forming, but this is not stable at neutral pH. So what will happen? One proton abstraction will happen, so it will form Fe OH H2O 5 3 plus, sorry 2 plus, then subsequently it will form 1 plus, and finally it will form Fe 2 step Fe OH thrice H2O 3. This is your final product. So basically it will precipitate as a ferric hydroxide. Okay, so the final product of the hydrolysis of FeCl3 is, sorry, option A is correct. Okay, so if it is clear, I will go to the next question. In the coordination complexes, the ligands are positively charged, negatively charged, or neutral, radicals, all of these. Can anyone just tell me, like, what will be the answer for the question number 14? Yeah, okay, yeah, this is a debatable question. In coordination complexes, the ligands are all of these. Anyone else has different opinion? Anyone else has different opinion? Let me go and explain. In coordination complexes, the ligands are. So the D answer is incorrect, because radical, till now there is no reports on radical where it can form like coordination complexes. In general negatively charged, or neutral. Neutral having lone pair. Lone pair are some kind of like CO, carbonyl, nitrosyl, others are there. But there is like, I don't know why they have put this option A. Very rare. One, I think only one is there, that is the nitrosonium ion, which form like coordination complexes. Very rare example of the like positively charged. So in general, like most of the time, your in coordination complexes ligands are either negatively charged or they are neutral. So the best suitable answer, if we have to choose one, so that option B is correct, which is negatively charged or neutral. Very rare, like in general, if we general thumbs up rule is that positively charged cannot form the like coordination complexes, but there is a rare example like nitrosonium ion where this can form the coordination complexes. So Devendra Malik, I think your confusion is clear. Like option B is correct. Like best suitable answer, I will say. Can you write in chat box that are you agreeing with me that okay, thank you. Let me go to the next question. The oxidation state of metal ion in VO4 3 minus and Cr2O7 minus. Can anyone write in the chat box what will be the answer, or just simply calculate it and let me know. Okay, Devendra Malik is saying B. Dr. Naveen Awasthi is also saying B. Okay, yeah. So yeah, both are correct. That option B is correct. Just let me solve it for others. So suppose the oxidation state of lead, oxidation state of vanadium is X. So we have X plus we have 4. Oxygen in oxide is basically 2 minus 2. What is the charge and the molecule or ion, which is minus 3. So X minus 8 is equal to minus 3. So X is equal to minus 3 plus 8, basically plus 5. So for vanadium it is plus 5. For chromium we can also suppose for the same, let oxidation state of chromium is X. So 2 into X plus 7 in oxides, oxygen oxidation state is minus 2 is equal to minus 2. So we have 2x is equal to 12, x is equal to plus 6. This is the correct. Okay, let me go to that. So TiO2 and this is subscript, Se2O3 are white because they titanium and scandium are not included in the transition element series. Energy levels splitting is high for transition to occur. Both are D0 electron system, hence no transition occur. Emission frequency of light fall outside of the visual. So can anyone write in chat box what is the answer for this question number 16? Okay, Devendra Malik is saying C. Anyone else? Okay, Dr. Naveen Awasthi is also saying C. Okay, so the correct option is C, because the first option is incorrect, because titanium and scandium are not included in the transition element. That is incorrect, because titanium 3 plus is a transition is a D1 system, and it is in the transition metal element series. But the most important thing about the transition element is they should be having the incomplete like field, or you can say that they should have at least unpaired electron in the D subcell. So but for titanium and scandium, this titanium 4 plus is basically D0 and scandium 3 plus. Here it is scandium 3 plus. Both are having D0 electron system. So if there is no D electron, so basically if we go to the crystal field splitting, either this is whatever it is, whether it is like tetrahedral or octahedral or anything, if it is not having any D electron system, then basically your transition will not occur and it will not fall in the visible region. So why these transition metal complexes are colored? Because their transition fall in the visible region. Once I will go to that color and electronic spectrum, I will go into the detail what is the molar absorptivity, what is the wavelength, like basically wave number in which they are forming. So all those things we will discuss in detail, but here at the first instant, because professor has discussed little bit about why this transition metal are colored, so on that only one question came in the why these things are not colored. Okay, because it is having no electron in the D subcell. So between two tetrahedral unit of dichromate ion, the angle is, this is I think like memory based question. So if anyone knows, they can answer, otherwise I will just go and tell you the answer, what is the answer. Can anyone just tell, like what is the, like between two tetrahedral unit, what is the angle? Basically it is asking the angle between CrO chromium bond. What is this angle? Okay, Dr. Naveen Avasthi is saying C. Anyone else? Okay, as obvious, it will not be the 90 degree, that is incorrect completely. 60 degree also not possible. So only 126 and 140. 140 is far from the, because this is looks like 120 degree. So for this reason you can just say, but it is a memory based question. So what is the angle between the two tetrahedral unit of diagram? So it will be close to 120 degree, that you can say here from. The correct option is C. I think Dr. Navi. So which of the following group of ligand are considered as the bidentate ligand? Na2 minus, SCN minus, CN minus, methylamine, EDTA, water, pyridine, NO, NCS minus, EN, OX, bipyridine. So EN is ethylene diamine, OX is oxalate, BYPY is bipyridine. Okay, so this Devendra Malik is saying option D is correct. Anyone else? Okay, ma'am is also saying that D. Okay, so yeah, so basically this Cn minus, we know that this is the Cn minus, and these two are MP dentate ligand, we have come across this. So they have two donor sites, but only one can donate at a time. They are monodentate ligand. NOT is monodentate ligand. In methylamine, only one donor site is there, that is lone pair of nitrogen. In EDTA, it is the it is a hexadentate ligand because it has 6 donor site, 2 nitrogen, 4 oxygen. Water has only one donor site, that is oxygen, because it has only 2 lone pair, but only one can be donated. Pyridine, pyridine is having one lone pair that can be donated. It has only one nitrosyl. Nitrosyl also has only one donor site. NCS minus is basically CN minus CN minus reverse. So in this only ethylene diamine. So what is ethylene diamine? This is CH2 N. So this have this bidentate. Oxalate also. Oxalate is basically C double bond O, C double bond O, O minus. So these two donor sites are basically O minus from the oxalate. Bipyridine is, so we have bipyridine is like this. Okay. So these two lone pair from 2 nitrogen can be donated. So the option D is correct because it is having bidentate property. Let me go to the question number 19. Which of the following complex is formed in the solution to give the blood red coloration? Can anyone tell? Which of the following complexes is formed in the solution to give the blood red coloration? Devendra Malik is saying okay. See, okay. Anyone else? Anyone else has different opinion than Devendra Malik? Okay, so the which of the following complexes form in the solution to give the blood red complex? That is the option number B is correct. So, Fe NCS water molecule 2 plus. So you have this, why this blood red coloration comes, what is the origin, that I will discuss in detail once we will go into the lecture where we have this color and optical spectra for the coordination complexes. Okay, I think let me go to the question number 20. The primary valency and secondary valency of the metal ion in the coordination compound CONH3 5Cl Cl2 is. Here also one more concept is there that I will tell you. Can anyone just write in the chat box what will be the answer for primary and secondary valency of metal ion in the coordination compound. Okay, Devendra Malik is saying B. Anyone else having different opinion? Yeah, that's what I'm expecting. Someone should say that A. Yeah, Harushan is also saying A. Okay. So, like, if we consider what Werner has said, then the option A is correct. The secondary balance is satisfied by basically anion or cation, whatever it is. But later, what people are saying actually what the primary valency is. So your primary valency of the metal ion is the oxidation state of the metal. So that is the key point to note. Like, later people has thought about it and given that the primary valency, which is ionic and non-directional, that is the definition what Werner has said. This primary valency is the ionic and the non-directional. So but people has thought that the primary valency is actually the what is the oxidation state of metal ion in the complexes, in the complex. Okay, so the correct option here, it is the +3 oxidation state, so 3 into 6. So if we see that primary valency and secondary valency for all the cobalt derivative, either whether it is NH3 6 5 4 3, whatever it is, the primary valency is the oxidation state of metal in the complexes. So the correct option is B. Okay, so with this I will just, yeah, that's the last question from assignment 1 I have. Okay, so let me go to keep. Okay, so yeah, let me switch on the video. Okay, so 1 minute, I will just switch up the recording.